formal, and if we were to do 5.1 to a T in your book, it would involve the definition of an integral using limits. Okay, which also involves something called summation notation. Okay, so we're going to focus on summation notation because that's a series and sequences thing that you will focus on semester 2. But I also want to give you kind of the idea of where an integral comes from. Okay, so I want to start with that. Like the limit definition of an integral at its broadest, the big idea. Okay, so let's just use an example, and we'll have an interval. Let's see, 0 to 3. So this is basically what we did yesterday. Can you calculate a right Riemann sum with 3 subintervals? Okay. So you can draw that up. You don't have to actually do the math right now. I'm going to do it in blue. That's what that would look like, correct? Okay. And then you could say, is that an over or an underestimate?
Over.
The right Riemann sum is an overestimate because?
F is increasing.
F is increasing, correct. Okay. How could you make that right Riemann sum more accurate?
Like make it a bit less increasing.
No, I mean like keep a right Riemann sum. How can we make that more accurate?
Add more intervals.
You can have more intervals. So let's say, right? Right? Does that look more accurate? Just in general? Okay. How could you make it more accurate?
More
Yeah, triple intervals.
Okay, so where is that number of intervals heading?
Infinity.
Bingo. Okay, so what you're seeing is an integral is literally, okay, so if we had like the integral from 0 to 3, okay, the limit as n approaches infinity of r sub n. Right, it's the right-handed Riemann sum with an infinite number of subintervals. That's the only way they would ever match the curve exactly, right? So that's the big picture. Make sense? Yeah, just make as many subintervals as you can and it gets more accurate. Okay. So that's one. So remember derivatives? How many definitions were there?
2.
There were 2 limit definitions. Guess what?
There's 2 integral definitions.
There are 2 ways to do integrals. Okay. The second one is a little bit more clunky, but it's just as valid. Okay. So let's do the same picture.
Is it just habit sake, or is there a reason why you're going for like, well, really stop at zero?
But what?
When you're doing the thing, is there a reason why you include the negative, like, just part of the thing, square, just out of habit?
It's easier to draw because you get the sweep instead of starting and drawing.
Is it a sweep or is it a scoop?
I call it a sweep. You might call it a swoop. I prefer potatoes.
Or is it a swoosh? It's not
Or
a
is it
swoosh.
swish?
No, there's
It's
an
definitely not a
X.
swoosh.
I prefer nothing but the bottom of the net.
Airball?
No, when it goes in the hoop, nothing but the bottom of the net. It's an expression you may not understand if you're not a basketball player.
Well, just logistically, I feel like that statement is wrong.
It's a statement in context that makes sense to basketball players.
Did you play basketball in high school?
Yeah.
Or in college?
Basketball.
Sense to me.
I should have played in college, but I didn't. I played football.
Neat.
My melon would probably be the better of it if I would have played basketball. Because I got hit a few times.
I know you're still doing calculus, so I say you're fine.
Things just aren't what they used to be. Okay, so here's the other way to do this. Okay, these have a size,
Right.
right?
Infinite?
And if,
Spoilers.
so what are we going to do to the size of that interval to get a perfect integral?
I mean,
You can expand it exponentially.
We call this the size x, right? The integral from 0 to 3 f of x dx is going to be the limit as x approaches what value?
Infinity?
You want the size of a rectangle to get
One.
0. What? So if you take the size of this and make it smaller and smaller and smaller, you just increase the number of intervals, right? It's the same concept, you're just using a different variable. So you're taking the size to 0, and you still have a perfect answer. So those are the two competing definitions, right? So the limit as the size goes to 0 of, no, it's still going to be n.
wait, then it would be as n approaches 0?
Yeah, that's why I'm confused.
No, because n is still the number of subintervals.
Oh, we assigned x as it.
So it's, like I said, it's a little bit more clunky, right? But you get the big idea, right? Like, that's all I'm gunning for here. I'm not going to ask you to do any problems because they're really messy. Big. Like, big. Half sheet of paper big.
Oh, no.
And you have to memorize these like nasty formulas. Okay, so that's where integrals come from, based on limits, just like derivatives. Okay? Let's talk about summation notation.
Look at the version of these, whatever.
What?
I don't know how much I agree with that.
I don't at all.
This is not health class, so we're not talking about reproduction. Okay. Okay. That's a sum, correct?
Mm-hmm.
Right?
Okay. When we do summation notation, we have a way to write that as a formula. Okay. Using the Greek letter sigma, the capital sigma, in fact.
The E.
Yep.
It's happening, guys.
The fact that there's a difference between sigma and big
It's a capital sigma, and if you want to be perfect, you're going to put
Thank you,
little
Kenzie.
tails on it.
And you got to throw it.
Those don't bounce.
They don't.
They bounce, but
Not very well.
okay.
Either way,
So-
it's okay.
If we're going to write this as a formula, what is my starting value?
0.
No,
No, 1.
1. So from I equals 1, okay, that will be our start.
It's starting to sound like a 4.
What's our end?
5.
5. Okay, this is a very simplistic one. And how would I get from 1 to 5?
You add all the values up to 5.
Yeah.
What?
Okay. Oh, that's not good. That's not good. I. Okay, so this is telling us to sum every integer from 1 to 5. So you remember what the integers are?
1, 2, 3, 4, 5.
Whole numbers, positive or negative, right? So start at 1 plus, what's the next one?
2,
Is it inter or inter?
Plus.
Okay.
3,
Plus
4, plus 5.
equals something, right?
15.
15.
Okay. That's how we would write that as a sum in summation notation.
So would we write what is it, sigma I equals 15, or would we write sigma I equals other than I equals 15?
Oh, you don't have to show your work on that one. That's fine. Equals 15 is good. Okay. How about a different one? From n equals
That's much easier.
0 to 4 of 4n squared.
What were you doing?
I wrote the E, I believe.
So we can change the formula,
That looks
right?
Oh, so you're adding all the values when n is
4 times 0 squared plus,
Oh, 4 times 1 squared plus 4 times 2 squared, so on and so forth.
Ooh. That's neat.
okay? Yeah. And so whatever that is. 4 plus 16 plus,
Is there a calculator in for this?
oh,
So it
Sum of,
goes
right?
to the 3, it doesn't go to 4.
most of these will not be calculator friendly.
Really?
Yeah.
Why?
So it only goes to the 3. I mean, it's just addition. Right?
Also, don't you go to 4 times 4 squared?
Oh, yeah, I did this. Okay, so you can get that sum, right?
Yeah, one thing, there is summation.
Oh, there is a summation notation on the calculator.
Math 9.
Math 9
That doesn't sound right.
is an integral. Correct me if I'm wrong.
Math 0, sorry.
Okay. 890. Got it. All right. Okay, that's summation notation at its basic form. Okay. We will be asked
Yeah,
to
120.
both generate these, like we did here, and to calculate answers to these, as we did here. And so sometimes you're given the sum, sometimes you are not. Okay, but that's summation notation at its basic.
How do you work it backwards if you're given the sum? and you
So if
go
you're
back?
given the sum, you have to find a formula that relates those terms.
Wait, would they give us the sum as in like the sum of each number that add?
They would
together?
give you this.
Oh, okay, so they
And
would give us
say,
like 15.
Write in summation notation.
Okay.
You would have to figure this out.
I thought you were saying they'd give us like just a number, you're like, right, summation.
No. They would give you a series. This is called a series.
So if you give it a series, and just look at the formula that creates the function.
Yep. So you don't always have to start at 1 or 0. When we study series semester 2, we will pretty much always start at 1 and 0. You can start at 2, 10, whatever. End at whatever. Okay. Where we're headed with this is Okay, something like this.
What's the purpose?
Is there a sum to that? Because what do you see there?
Wouldn't it just be 0? That's like the limit is.
No, because you have, oh, we have to start. Sorry, let's start here. 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4.
Until infinity.
Okay. The question is, does that actually sum up to a number? Or does it diverge and just go to infinity? Okay, that's what we study semester 2, is different ways to calculate sums or divergence of these.
So what's the purpose of this? Like,
So wait.
actually, what does this do for us?
Today,
No, like, what's the purpose of the summation?
summation notation. There's a lot of recursion in it. And computers and recursion are a big deal. Okay, so that's number one. And it's just practicing that in a different context. Okay. A lot of engineering works with bounding, upper and lower bound. So you'd have, say, a beam in a room, right? A support beam for the ceiling. There's a minimum amount of load that you want that to support, right? You don't want to design that beam for that lower bound. You want to design it so that not only can it support that lower bound, but there's an upper limit that it can support. Like, say you have a roof and the snow is falling gently and it puts 40 pounds per square foot on there. You want that to support that, right? But you also want it to support, let's say, a 40-pound dog jumping on the roof. That creates more force, right? So there's an upper bound that you want to design that for too. So there's kind of a range of values there.
So that helps you find that.
So this just helps you, no, obviously the calculus is going to be a little different than this, right? But it gives you the problem solving and the brain framework to work in that. It just helps. Does that make sense?
I'll accept it.
Okay, I'll just leave it there. This, in fact, is called the harmonic series.
That specific example, right?
Yeah. Will that ever be important? That diverges to infinity when you add all the terms up.
Wouldn't anything to infinity diverge?
Nope. Here's one that does not.
So, yeah, if it was just n to infinity, the answer would be negative 1. Why? I'm not entirely sure. But
That converges.
To 0?
Okay, what it means is it has a sum.
What?
I don't know. I don't remember.
So, but how can it have a sum if you just keep adding forever?
Yeah, but what you have is eventually the numbers get so small
That it just,
that it never crosses some upper bound. It gets closer and closer to that. It's like a
Okay.
horizontal asymptote.
That's what I was expecting
Yeah.
for the first
Right.
one, but it doesn't happen in the first
Nope.
no.
Weird, right?
I hate
one. Because I was expecting the first one to never go past 2.
Oh, it definitely goes to infinity. It's been proven.
Whack.
So what does it mean by the harmonic series?
That's just what we call it.
Okay.
What's the sum of the second one?
I don't remember.
That you
I don't even know if we've ever computed it. No, it's bigger than 2.
There's probably some supercomputer that's been working for like 5 years.
Chapter 10.
It has like 1,000 terabytes of just significant numbers.
So if you look at chapter 10, you'll see a whole bunch of series problems.
So would it technically have a sum or just like an asymptote?
We call that asymptote the sum.
Oh, we do?
Yeah.
But it never
It's
actually.
the upper bound. It would never actually get there, but it would get so close that it doesn't matter in any application problem.
So is there another way to find asymptote?
So we would actually be able to calculate that error, right? Because one of the things in calculus is calculating the error at any number of terms out. So, you know, engineering is all about being within your error. Right? You can tolerate so much error or so much upper and lower bound. I mean, it's all there.
I think once we
And
apply math skills, it's-
I do not see,
Yeah.
What do you mean when? We should be doing it now for engineering.
And
you won't, I don't think you'll ever do this in an engineering project.
Probably not.
You'll
but
just use the brain power.
What calculus are you using in making a pond?
Just basic.
Cross-sectional area and volume.
You just do volume, since you have like a square tile or whatever. You
not the way
cross
he's
section.
doing it.
I do not know
Three different sections, it's faster.
what the sum of that is.
Shut up. What's the scale of
Okay.
Yeah, that's a good question. How big are you making your pond?
it? It's 18 feet across.
Okay, so I'm gonna stop the video, but,
Are you actually gonna build it?
oftentimes it's kind of funny. We're not concerned with what that actually adds up to. We're just concerned, does it?
Question, while we're talking about like adding to infinity, do you know about the string theory thing that says if you like did summation notation for starting at 0 and going to infinity and adding them up out equals -1/.
Let me write this down and then I can actually listen to you, because string theory is way out there,
You're amazing.
if it's true.
True.
That's what it's called theory.
Exactly.
But, I
I
mean,
feel like evolutionary theory, it's not a law, like gravity,
gravity's a
definitely a law.
Really? Let's try
String
this
theory.
out. Okay, gravity's good.
Okay, they are, this is not a lot of work because they're very basic problems.
Sweet.
well, because when you get into string theory, you gotta start thinking about like what's smaller than a quarter.
Oh, what?
There's obviously something in these.
Oh, the